All right. So you know how we use numbers like all the time, right?
Yeah.
But have you ever like stopped and wondered what they really are? I mean, are they like actual things out there, like kind of like that chair you're sitting on,
Yeah.
in some like abstract world of math? Or are they more like super useful ideas we've come up with to understand things?
Yeah, that's a really good question. It's something that philosophers have been debating for a long time.
And today we're diving into a way of looking at math called structuralism
Mhm.
that gives us like a pretty mind-blowing answer.
It really does kind of flip things on their head. See, when most people think of math, they picture like numbers and shapes and equations. It feels like we're dealing with like solid things we can define, right?
Right, right.
But structuralism says that what's really important isn't the individual things themselves, but like the connections between them, the structure they form. It's like, instead of focusing on a single Lego brick, you're looking at the instructions and the whole thing you can build with them.
Okay, so let me see if we get this. So like instead of saying the number two is this one specific thing defined by like some complicated set stuff, structuralism says it's more about like how two behaves within the whole number system, like how it comes after one and before three, how it works with addition and all that.
Exactly. It's about its role in the overall system.
So this deep dive is going to be all about tracing how this whole idea developed. We'll start with like some major challenges to the old ways of thinking about math and then explore the different types of structuralism that have emerged.
And what's really cool is that this isn't just some abstract philosophy stuff. Understanding structuralism can actually help you see how mathematicians think and work. It explains why they're so obsessed with patterns and relationships and why certain ways of doing math are so powerful.
So we're going to start by going back in time to some pretty heated debates in the 1960s and then work our way forward to some really fascinating modern viewpoints.
A wild ride.
Now you, our listener, are someone who wants to get to the heart of the matter right without getting bogged down in too many technical details. And that's exactly what we're going to do.
Yeah, we'll try to keep it clear and engaging.
So get ready to have your ideas about the seemingly solid world of math, like totally turned upside down.
All right, so to kick things off, let's set the stage. We're back in the 1960s. Before structuralism really took hold in philosophy, what was the prevailing idea about how math was built? What was considered the foundation of it all?
So back then, the dominant view was that everything in math rested on something called axiomatic set theory. It was like this. Mathematicians thought that every concept in math, from the simplest number to the most complex theorem, could be defined and explained using sets.
Like sets were seen as the building blocks of math, right?
Right. So, for example, the natural numbers, like 0, 1, 2, 3, and so on, were often identified with specific sets called the von Neumann ordinals. 0 was defined as the empty set. 1 was the set containing the empty set, and so on. It gets a bit complicated, but the idea was that every number could be represented by a specific set.
So when you said something like 2 plus 3 equals 5, it wasn't just a statement about abstract numbers. It was really a statement about these specific sets.
Exactly. And this seemed to provide like a really neat and tidy foundation for all of mathematics. But then in 1965, a philosopher named Paul Ben-Asaraf came along and wrote a super influential paper called What Numbers Could Not Be, and it kind of shook things up.
Yeah, Ben-Asaraf's paper is considered a classic in the philosophy of mathematics. What was his main argument? What did he point out that challenged the set theoretic view?
Well, he did something really clever. He pointed out that there isn't just one way to define numbers using sets. You could use the von Neumann ordinals, like we talked about, but you could also use something called the Zermelo ordinals, which define the next number in a slightly different way.
Right, you still start with the empty set for 0.
Yeah, but then the next number is just the set containing the previous number.
Ah, I see.
And here's the thing. Both of these systems and many others work perfectly fine as representations of the natural numbers. They all follow the basic rules of arithmetic.
So if there are all these different ways to represent numbers using sets, what did Ben-Asaraf conclude from that? What was his big takeaway?
He argued that if numbers could be represented in so many different ways, then they couldn't actually be any one of those specific sets. It's kind of like saying you can make a chair out of wood, metal, or plastic. So the essence of chairness isn't tied to any specific material.
I see.
For Ben-Asaraf, the key thing about numbers wasn't the specific set used to represent them, but the relationships between them. The order, the connections, not the stuff they're made of. He famously said the numbers are positions in structures, not objects themselves.
That's a really important point. So for our listener, if you had to remember one key idea from Ben-Asaraf, it's that the role a number plays in the system is more important than what it's made of.
Now, right around the same time in 1967, another philosopher, Hilary Putnam, weighed in on this debate with a paper called Mathematics without foundations.
Right. Putnam was also pretty skeptical about the idea that set theory was this absolute foundation for math. What was his take on all this?
Well, he had this idea called if-thenism, which is a way of looking at math theorems as conditional statements about models of axioms.
Okay, can you give us a simple example of how this if-thenism works? How would he analyze a basic math truth?
Sure. Take something simple like 2 plus 3 equals 5. According to Putnam, this isn't about specific numbers being objects. Instead, it's like saying, if you have a system that follows the rules of arithmetic, what are called the Dedekind piano axioms, then in that system, the thing that acts like 2 plus the thing that acts like 3 will result in the thing that acts like 5.
So it's more about the logical consequences within any system that behaves like arithmetic.
Exactly. It's not about the intrinsic nature of the things involved, but about how they relate within a system.
Now, Putnam also introduced this idea called universalist structuralism. What was that all about?
Well, his universalist structuralism took this even further by saying we should really be talking about all possible systems that have a certain structure. So instead of looking at just one specific model of arithmetic, you're talking about something that holds true across any system that has those same structural properties.
Okay, that makes sense. But there's this common worry about if-thenism called the non-vacuity problem. What's the concern there? What's the potential issue with saying math truths are just conditional statements?
The worry is that if-then statements are always true if the if part is false. So if there were no systems that actually satisfied those Dedekind piano axioms, then saying if you have a system that follows the rules of arithmetic, then 2 plus 3 equals would be true even if 2 plus 3 didn't equal 5 in any real sense.
It's like saying if unicorns exist, then they have horns. That's true even if there are no unicorns. It doesn't tell us anything about actual horned creatures.
Right, so it's like the statement becomes meaningless if there's nothing for it to apply to. Even something totally nonsensical, like if you have a system that follows the rules of arithmetic, then 2 plus 3 equals 6 would be technically true if no such arithmetic system existed.
That's a really clear explanation. Now, Putnam suggested that modal logic, the logic of possibility and necessity, might help get around this problem. But he didn't fully develop that idea, so this left an opening for other philosophers to build on these initial insights and try to come up with more solid structuralist views.
Absolutely. The 1980s and 90s were a really exciting time for structuralism, as philosophers wrestled with the implications of what Benesaraf and Putnam had started and tried to flesh out more complete theories.
And this led to some really interesting developments. One key figure during this period was Michael Resnick. How did he approach the idea of mathematical structures?
Well, Resnick was on board with Benesaraf's idea that math objects are essentially positions and patterns. But he went a bit further and said, this view allows us to take mathematical statements at face value. When we say 0, 1, 2, we're actually talking about those specific spots in the overall pattern of natural numbers. However, he was a bit hesitant to fully reify these underlying structures.
Now, when you say reify, what does that mean in this context? What would it mean to reify a mathematical structure?
To reify something abstract, like a structure, would mean to treat it as if it were a real concrete object with its own independent existence, like it has to have clear rules for when it's the same as another structure and all that. Resnick wasn't so sure about that. He was wary of saying these structures are real things out there.
He was more cautious, right?
Right, he even quoted the philosopher Quine, who said, no entity without identity. Basically meaning if we don't have a clear way to say when two things are the same, then we should treat them as real separate entities. So Resnick was more focused on the how we know side of things, how we come to grasp these patterns.
Now, in contrast, another philosopher, Stuart Shapiro, took a much more realist stance. How did his anti-REM structuralism differ from Resnick's more careful approach? And what does anti-REM even mean?
So Shapiro also believed we should take math statements at face value. But he argued that abstract structures actually are real objects existing before the thing. Anti-REM is Latin for that.
Yeah.
And it comes from medieval philosophy where they talked about universals. He saw structures as having a kind of double nature. They're universals in the sense that many different systems can embody the same structure, like we saw with the von Neumann and Zermelo ordinals, both capturing the natural numbers. But they're also particulars, individual things that can be named and studied on their own. To support this idea, Shapiro even developed a formal structure theory, basically a system of axioms to describe which structures exist and when they're the same, all without relying on set theory.
So the key difference is that Shapiro was totally fine with saying these structures are real objects, whereas Resnick was more focused on them as patterns that we recognize.
Right. Now, around the same time, Jeffrey Hellman offered another take on structuralism, and he was explicitly anti-realist. What can you tell us about his modal structuralism and how it differed from Shapiro's view?
Well, Hellman took Putnam's if-thenism and incorporated modal logic in a much more rigorous way. For him, a statement like 2 plus 3 equals 5 isn't about actual numbers or abstract structures existing out there. Instead, it's analyzed as necessarily, if any system follows the basic rules of arithmetic, then the element in that system corresponding to 2 plus the element corresponding to 3 will equal the element corresponding to 5. And remember that non-vacuity problem. To avoid that, he added the assumption that it's possible for such an arithmetic system to exist.
So what was Hellman trying to achieve with this modal approach? What was his main goal?
He famously aimed for what he called structuralism without structures. He wanted to get away from saying that abstract structures exist as separate things like Shapiro did. He thought the modal parts, the necessarily and possibly, could do all the work. This view was also meant to be a form of nominalism, which is a philosophy that tries to avoid saying abstract things exist at all. So it's structuralism because it's all about the relationships, but without structures, because it tries to do away with structures as independent entities.
Now, this back and forth between Shapiro saying structures are real and Hellman trying to get rid of them led another philosopher, Charles Parsons, to come up with a handy way to categorize these different structuralist views. What were the two main categories he identified?
Parsons distinguished between eliminative structuralism, like Hellman's, which tries to eliminate structures as separate things, and non-eliminative structuralism, like Shapiro's, which embraces them as real. Later, Hellman described this as structuralism without structures versus structuralism with structures. And interestingly enough, Parsons himself, along with another philosopher, Charles Chihara, also became proponents of non-eliminative and eliminative structuralism, respectively.
It's important to keep in mind, though, that even within these two broad categories, there's a lot of variation. Shapiro's anti-REM structuralism is often seen as the prime example of non-eliminative structuralism, and Hellman's modal approach is a major eliminative view, but they're not the only games in town. Parsons' own position is a good example of that.
Right. Parsons argued that our understanding of structures should come from how mathematicians actually do math, not from some philosophical theory imposed from outside. He thought abstract structures are introduced through what are called categorical axiom systems, which are basically sets of rules that define a certain kind of structure. And he was against saying things like, the number 1 in the natural numbers is the same as the number 1 in the real numbers. He called these cross-structural identifications and thought they were kind of fuzzy and not how mathematicians really think.
Like Resnick, his view was a bit less realist than Shapiro's. You could believe in structures without necessarily saying they exist in some Platonic realm.
Right. But the basic idea that math statements are about something real, even if that something is a structure, was still there.
Now, as we move into more recent times, from the late 1980s to today, things have gotten even more complex and interesting, with new ideas and challenges popping up all over the place.
Yeah, the last few decades have seen a lot of scrutiny of structuralism, especially the kinds that say structures are real things. This has led to some pretty tough metaphysical and epistemological challenges.
So what are some of the big questions that philosophers have raised about structuralism? What are some of the major criticisms?
One major challenge that emerged around the year 2000 is the identity problem. The basic idea is that in certain structures that are symmetrical, like the complex numbers, where you have I and II, both of which square to -1, or even a simple graph with two unlabeled dots connected by a line, you have objects that are structurally identical. If all that matters is structure, shouldn't these be considered the same? This posed a problem for structuralists who said structures are real things because it suggested their view couldn't distinguish between things that seem distinct.
Makes sense. If you only care about the pattern, and two things perfectly fit that pattern, are they really different? So how have structuralists responded to this identity problem? What are some ways they've tried to address it?
Well, they've come up with a few different responses. One approach is to try to rigidify structures by adding more specific features to distinguish between those seemingly identical objects. Another is to argue that identity is a fundamental concept that we just have to accept as basic, similar to how it's often treated in math itself. But these responses haven't totally satisfied the critics, and the debate is still going strong.
Another big challenge questions the whole idea that mathematical objects only have structural properties. What's the argument there? Why would someone object to that?
The objection is that math objects and structures seem to have properties that aren't just about their place in a structure. For example, the fact that the natural numbers are so useful in describing the world that usefulness isn't part of the structure itself, it's something we observe about how it relates to other things. Or take the number 8. The fact that there are 8 planets in our solar system seems like a non-structural property of the number 8. So the question is, how do we even tell what's a structural property and what isn't? It's not always so clear-cut.
And that sounds like a pretty tough line to draw, doesn't it? Where do you even begin to separate those things?
It's tricky. Structuralists have tried to define structural properties as those that are essential to a structure or those that are preserved when you map one structure onto another, but it's proven to be a really difficult issue to resolve.
Then there's this idea of ontological dependence. How does that relate to structuralism?
From a structuralist perspective, individual math objects only make sense as parts of a larger structure. So the number 2 only exists and has meaning because it's part of the whole structure of natural numbers. This raises questions about how we understand this dependence. Does it mean the structure is somehow more fundamental than the objects themselves? And how does this fit in with broader ideas in philosophy about what it means for one thing to depend on another?
And of course, there's the big question for anyone who thinks abstract mathematical entities exist, especially if they exist independently of us, like some structuralists believe. How do we actually know anything about them? This is the access problem, right?
Oh, exactly. The access problem asks how we as physical beings in the world can gain knowledge of abstract structures that are supposed to be outside of space and time. This is a classic problem for any view that believes in abstract objects. Some structuralists, like Resnick Shapiro and Parsons, suggest that we posit or assume the existence of structures based on the axiomatic theories that describe them. But then the question becomes, when is it okay to just posit something? What makes that a legitimate way of knowing?
So what do they point to as a justification for positing these structures? What makes it a reasonable assumption in their view?
A common response is to appeal to the coherence of the axiomatic theories. Since Gödel's incompleteness theorems showed that we can't always prove a system of axioms is consistent within that system itself. Coherence, meaning it's internally consistent and doesn't have obvious contradictions, is often seen as a good indicator that we're on the right track. Interestingly, even though they have very different views on the reality of structures, both Shapiro, who believes they exist, and Hellman, who tries to avoid that, have both emphasized this idea of coherence as a basic requirement for either the existence or the possibility of mathematical structures. It's a surprising point of agreement between these two seemingly opposing views.
It is fascinating that they converge on that point, despite their different starting points.
Mhm.
So beyond these challenges, it sounds like the landscape of structuralism has become even richer, with a whole bunch of variations on the theme emerging.
Absolutely. Shapiro and Hellman's approaches aren't the only ways to think about structuralism. Over time, a lot of other ideas have popped up, some with roots going back even before the big debates of the 1960s.
So what are some of these other takes on structuralism? What are some alternative viewpoints that have been developed?
One important category is set theoretic structuralism. You know how Ben Asaraf pointed out that there are multiple ways to define numbers with sets? Well, set theoretic structuralism agrees that it's wrong to say the natural numbers are exactly the same as any one specific set theoretic construction. But it says for practical purposes, we can still choose one system, like the von Neumann ordinals within ZFC set theory, and use that as our representation. So talk about numbers is then seen as relative to this choice. The structuralist part comes in because we're essentially indifferent to which system we choose as long as it captures the right relationships. There's also a more general version that allows for basic objects that aren't sets, which is called relativist structuralism.
So it's like picking a specific brand of measuring tape, even though, there are other brands out there.
Yeah.
As long as it's consistent, it works for doing measurements.
Exactly. Now, another interesting viewpoint is concept structuralism. What's the focus there?
What's that one all about?
Concept structuralism shifts the focus away from mathematical objects themselves and towards the concepts behind them, like the concept of a natural number system, as defined by those Dedekind-Peano axioms we mentioned earlier. The main idea is that what really matters is what logically follows from these concepts from the rules that define them. Talk about specific objects is seen as secondary, maybe even something that can be explained away altogether. This view actually has historical roots going back to the 19th century with mathematicians like Hermann Grassmann.
Now, we've also got something called abstractionist structuralism. What are the different ways of thinking about that one?
There are basically two paths within abstractionist structuralism. One says that a structure is basically the collection of all systems that fit a certain concept. So the structure of natural numbers would be like the class of all systems that satisfy the Dedekind-Peano axioms. This idea has connections to philosophers like Rudolf Carnap and Bertrand Russell. The other path, which comes from Richard Dedekind, involves starting with a concrete example of a structure like the natural numbers as we normally think of them, and then abstracting away from the specific nature of the individual elements. You're left with a pure abstract structure that's just about the relationships. This is actually pretty similar to Shapiro and Parsons' views, but it gets there through this process of abstraction. This often involves these ideas of abstraction operators and abstraction principles, and it even connects to a whole program in philosophy of math called neologicism.
It's amazing how many different angles people have come up with for thinking about mathematical structure. And it sounds like even in recent years, philosophers are still finding new ways to explore it.
Definitely. In the 21st century, we've seen philosophers using different background theories other than standard set theory to develop non-eliminative structuralism. For example, Edward Zalta and Bernard Linsky have used their axiomatic objects theory. Kit Fine has used his theory of arbitrary objects, and Hannes Leitgeb has even used graph theory as frameworks for understanding structures.
So we've been talking a lot about structuralism as a philosophical idea, but
Yeah.
there's also this distinction to be made between that and what's called methodological or mathematical structuralism. What's the difference between those two?
That's a key distinction. Metaphysical structuralism, which is what we've been mainly talking about, is about answering those big philosophical questions. What are mathematical structures? Do they exist? What makes them the same? How do we know about them? Methodological structuralism, on the other hand, is about how math is actually done. It's a way of doing math that emphasizes the overall structure and the connections between things, often using axioms and focusing on mappings that preserve structure while paying less attention to the specific nature of the individual objects.
And this way of doing math has actually been around for quite a while, hasn't it?
Oh, yeah. Its roots go way back to the 19th and early 20th centuries, with mathematicians like Dedekind, Felix Klein, David Hilbert, and that famous Bourbaki group in France. They all emphasize this structural approach. Today, the two main ways this methodological structuralism is expressed are through set theory and category theory.
And we can even think of this methodological structuralism as having different levels, right?
Exactly. At the most basic level, it's about defining structures, using axioms, and proving theorems about them, like Dedekind and Peano did with the natural numbers. A second level involves studying the relationships between structures, using things like homomorphisms and isomorphisms, which are ways of mapping one structure onto another while keeping the key relationships intact. A third level aims to classify all the different kinds of mathematical structures and how they relate to each other. That was a big goal of the Bourbaki group with their mother structures idea, and it became central to category theory later on. And a fourth, more advanced level involves taking theorems that have been proven in one structural context and applying them to other related structures. These are often called structure theorems.
So this focus on methodology really shows that structuralism isn't just some abstract philosophical idea. It's deeply connected to how math is practiced and understood.
Absolutely. And this development of structuralist methodologies was a huge factor in the rise of modern mathematics. Which brings us to category theory, which some have proposed as a really powerful framework for structuralism.
Yeah, category theory has been put forward as a potential foundation for this whole structuralist view of math. What is it about category theory that makes it such a good fit?
Category theory, which came about in the mid-20th century, is a very abstract way of looking at structures. It focuses on objects and morphisms, which are arrows that represent relationships between these objects. Unlike set theory, which starts with sets as the basic building blocks, category theory takes these relationships as the fundamental thing. People like Steve Erode argue that category theory captures the spirit of structuralism really well because it emphasizes when objects are essentially the same, it's independent of how we write things down, and it really focuses on those structure-preserving mappings. So instead of asking, what is this object made of, you ask, how does this object relate to other objects?
Now, Audi even makes this distinction between using category theory for mathematical structuralism versus using it for philosophical structuralism. Can you explain that difference?
Right. So for mathematical structuralism, category theory gives you this awesome language and tools for actually doing math in a structural way. For philosophical structuralism, it's put forward as a framework for understanding the whole nature of mathematical reality and how we know about it from a structuralist perspective. So it can be both a way of doing math and a way of thinking about what math is.
But this idea of category theory as the foundation for all of math has definitely caused some controversy. Some people have questioned whether it can really stand on its own without relying on set theory in some way.
Yeah, that's a big debate. Jeffrey Hellman, building on work by Solomon Pfefferman, brought up the logical dependence objection.
Hmm.
The idea that category theory ultimately needs set theoretic ideas like collections and functions, and the mismatch objection, which questions whether category theory, being so general and schematic, can really be a precise foundational system in the same way that set theory aims to be.
But folks who support category theory as a foundation like Colin McClarty argue that certain versions of it can be seen as autonomous from set theory. What do they say?
Well, McClarty argues that systems like Lauver's ETCS define sets based on their relationships and how they map to each other, not by what elements they contain. He sees this as a more inherently structural way of thinking about the foundations. On the other hand, some like Steve Awudu himself take a more anti-foundationalist view. They say category theory's strength isn't in being a foundation for all of math, but in providing a common language that lets us connect and understand different structures without getting bogged down in those traditional foundational debates.
So regardless of the foundational stuff, it sounds like category theory brings some pretty important philosophical ideas to the table that mesh well with structuralism.
Absolutely. For one, it tends to see math theorems as statements about patterns themselves applicable to any structure that fits the pattern. It also gives us a top-down way of understanding mathematical objects based on how they relate to other objects rather than building them up from the bottom, like in set theory. And many argue that category theory really embodies the structuralist idea that all the important properties are structural, meaning they're preserved when you have isomorphic objects, which are objects that have the same underlying structure. Basically, if two objects have the same structure, category theory treats them as the same for all intents and purposes. McClarty even says that Benacerraf's dilemma about those different but structurally identical number systems doesn't come up in categorical set theory because those systems would be considered truly identical.
That's really interesting. So by focusing on the relationships, category theory might actually sidestep some of the classic philosophical problems in math.
It's a compelling idea, but some, like Semensi, still question whether even these categorical approaches truly give us a fully structuralist foundation. It's a really active area of research, with other frameworks like Mackay's fold S and homotopy type theory being explored as well for their structuralist potential.
It's amazing how this one idea of focusing on structure has led to so many different and complex ways of thinking about math. Now, before we wrap up, we mentioned earlier that structuralism isn't just confined to the world of math. Can you expand on that a bit?
You got it. The idea of understanding things in terms of their relationships and structures has had an impact on other fields as well. For instance, in the philosophy of physics, there's this view called structural realism, which explores the idea that what our best physical theories really tell us about the world are its underlying structures. This relates to how we understand those fundamental entities in physics and what remains constant even as our theories change. And in the humanities and social sciences, particularly in fields like linguistics, anthropology, and psychology, structuralist approaches have been influential too. Though the connection to mathematical structuralism is often more metaphorical and has sometimes been associated with ideas of underlying psychological frameworks. A good example is the anthropologist Claude Lévi-Strauss, who was influenced by the structuralist ideas of the Bourbaki group.
So to wrap up our deep dive into structuralism, what's the main thing you think our listeners should take away from all of this?
The key takeaway is that structuralism represents a major shift in how we think about math. Instead of obsessing over what math objects are in some absolute sense, it focuses our attention on the abstract structures they belong to and the connections between those structures.
And as we've seen, it's not just one simple idea. It's a whole family of views that has developed and evolved a lot since the 1960s, with many different versions trying to tackle deep questions about the nature of mathematical truth, how we come to know it, and how math is actually practiced.
Exactly. And that methodological side of structuralism has had a huge impact on how modern math has developed.
So here's a final thought for you, our listener, to ponder. If mathematical truth is really all about these abstract structures, what does that tell us about the nature of reality itself? Especially when we consider how structuralist ideas have popped up in physics and other sciences. Could it be that those patterns we discover in math are actually reflections of a deeper structural reality that goes beyond just the abstract world of numbers and shapes?
It's a question that's worth thinking about for sure. And if you're interested in exploring structuralism further, we encourage you to delve deeper into some of the areas we've talked about today. Maybe the identity problem, the different types of abstraction, or the debates about category theory as a foundation. It's a fascinating journey into the core of mathematical thinking, and there's always more to discover.
Absolutely. Well, that's all the time we have for today. Thanks for tuning in to our deep dive on structuralism.
It's been a pleasure.
Until next time, keep those brain gears turning.
And keep exploring the fascinating world of math and philosophy.